Okay, good afternoon. So this is where we left off last time. On the board is the chart of the problem we're trying to solve, having lots of different data types and lots of different operators, and that gives rise to m times n different ways to do things, and trying to keep a handle on all of that. And we've looked at two different organizing principles. The first one was take vertical slices through this table. And this the book calls conventional programming, again, because this is how you do it if you don't think very hard, because of that noun-verb distinction that everybody has in their brains. So we organize around the verbs, and we write a procedure area that has built into it all the area formulas for every possible shape. That's not so good, because if we want to add a new shape, we have to go edit a bazillion procedures, and we're bound to introduce bugs in things that used to work. So instead, we have this idea of data-directed programming. And up in the top half of the screen, you see data-directed programming as we're using it to solve this problem. And just to remind you, on the bottom half of the screen, we see a chunk of a completely different way of using data-directed programming in order to automate the writing of compilers for programming languages. So instead of having to write each compiler from scratch, we write one generalized compiler. It's an extreme example of generalizing patterns that I talked about back in week 2 when we introduced higher order functions. And started with generalizing the pattern of finding areas of shapes by introducing an extra variable that says what the shape is. This is an extreme example of generalizing patterns where we just build one compiler that can compile any language by virtue of an auxiliary data file like this one in the bottom half of the screen that describes the syntax of whatever particular language we're trying to compile. And so these days, every specification for every programming language has an appendix that says, here's the BNF for this language, and it looks something like what you see on the screen there. I just should point out that we're kind of privileged in having procedures as a data type in our language, because we can put in the table a direct executable representation of what it is we want to do. In this other kind of data-directed programming, exemplified by what's on the bottom half of the screen, you have to write some more software to take this notation, which is just, strings of characters, and turn it into something executable that actually compiles your program. And for us, the only function like that we need is this little 5-line operate procedure where the cursor is blinking that looks up the thing in the table, and if it finds something, it just invokes whatever it finds directly on the operand. Okay, so that's kind of nice, and it makes data-directed programming particularly easy for us, so easy that it probably doesn't feel like much of a big idea. And that was the other reason I wanted to show you the BNF thing, to impress upon you not only that it's a more general idea than just solving this particular problem, but that it really is a big, complicated, it was a big step forward in thinking about computing when they invented it. Okay, so if you look at this chart and you see, okay, there's one way to take the whole chart as data, and there's another way to do this by making vertical slices. It's bound to occur to you, what happens if we make horizontal slices through the table? I mean, it sounds like a pretty strange thing to do, but once you have this idea of slices, what about that kind of slice? That's our next big idea. It's called message passing. And let me show you how it works. Oh, first of all, just as a reminder, we had these two procedures, area and perimeter, that merely call the operate procedure as a kind of syntactic sugar. Notation, something that's purely notational that we don't need to do the job, but it just looks more like what users want. That's called syntactic sugar, and it led to the famous aphorism by Alan Perlis that syntactic sugar leads to cancer of the semicolon. So those of you who've programmed in other languages will understand. So oops. So in order to do message passing, we're going to change the way we create individual shapes in our system of notation. So for conventional and for message passing style, we just used the idea of tagged data. So we had something that looked like this. Square, that's the type tag, and 4, that's the side of the square. Okay, and that would be the shape. And now what we're doing is we're going to represent shapes as procedures. So if I say define S4 to make square 4, what's the value of S4? Well, it's a procedure. It is, to be exact, this procedure with 4 substituted for side. Similarly, I can say define S5 make square. Hardest part about this is spelling square. And I get a different procedure. It doesn't look so very different, but it's a little bit different. And it does behave differently because here we've substituted 5 for side in the 3 places where it appears here. Okay? So you've seen something like this before. Back when we introduced pairs, and I said, and the book said, we actually don't need to have pairs as a primitive feature of our language because we can implement pairs using lambda. Remember? So we said define cons of AB to be lambda of message. If the message is car, return A. If the message is coulda, return B. And we're doing the same thing here. We're representing a square as a procedure that takes a message as an argument, and then it says, if the message is area, and here's the formula for the area. If the message is perimeter, here's the formula for the perimeter. And similarly, oops, make circle is the same thing. It's also creating one of these message passing procedures, except that the formulas are different. They have pi in them. So instead of side squared, it's pi r squared, pi radius squared. And instead of side times 4, it's 2 times pi times radius. Okay? Any questions so far about how we're representing shapes? So I'd like you to convince yourself, first of all, that this way of representing shapes is, in fact, a horizontal slice through this conceptual table. That what we represent a square as something that knows all the formulas for all the operators on squares. In this simple example, there are only 2 of them, area and perimeter. And we represent a circle as a horizontal slice on the circle line that knows all the formulas for circles. So now what we have to do is figure out what happens. How are we going to make it work for me to say area S5 and still get the answer that I want? And the way that that works is really kind of beautiful. Here it is. It's a much simpler version of operate. The first operate wasn't very complicated, but this one's even simpler. Because an object now which is a square or a circle or whatever, is executable. It's a procedure. And so we just invoke it with the operator, which is a word, as its argument. So when I say area S5, what I'm really saying is operate, quote, area S5. And that in turn is saying invoke S5 with area as its argument. Okay, so all these three things that I've said on the bottom half of the screen are the same. Questions? Yeah. Okay, how is area defined? I inherited this old definition of area left over from data-directed programming. I don't have to change anything except for the operate procedure. So that's kind of cute. Good question, though. Any other questions? Okay, moving on. Why on earth would we want to do this? So one answer is now adding a new shape is easy. If I want to deal with hexagons, I don't have to go and modify the existing procedures at all. I just write one new procedure, make hexagon, that has all the formulas for hexagon in it. So if I'm adding a lot of data types and I'm not adding a lot of operators, this might be the way to go. Conventional programming, it's easy to add new operators. You don't have to modify any existing code. You just write a new operator procedure. And this is the opposite. But a much more interesting answer about message passing is that we're going to see next week that message passing is at the heart of something you've heard of and maybe used called object-oriented programming, which is the next big programming paradigm. So this is something we have to understand as a precursor to that. Who's used object-oriented programming before? A lot of you. Who knows anything about how it's implemented? How, they write a Java code. My TAs do, okay. That's good. So even those of you who used object-oriented programming before are not going to be bored as we start exploring it next week, because we're going to teach you how it's implemented. It actually turns out not to be very mysterious. So one of the goals of this course is to demystify the different programming paradigms and help you understand how they work. Okay, so that's message passing. The next thing we're going to do is go back to data-directed programming for a bit and talk about a problem that we've so far swept under the rug, which is a lot of times you have operators with two operands. Like, for example, minus. I'm choosing minus rather than plus because it's non-commutative, so it makes the issues a little clearer. So let's say I want to add a minus column to this table. I'm going to leave these blank. Squares and circles, you don't do minus on. But what we do minus on is numbers. Numbers, for purposes of today's discussion, come in 4 flavors. Integer, rational, real, and complex. Okay. So if I have 4 kinds of numbers, how many rows do I have to add to the table? It depends how I do it, is the answer. The most straightforward answer is 16. Because there's nothing that says that the 2 operands are going to be the same type. I can do integer minus integer, integer minus rational, integer minus real, integer minus complex. rational minus integer, rational minus rational, rational minus real, and so on. 4 kinds of first operand times 4 kinds of second operand is 16 lines we have to add to the table. And furthermore, the labels over on the left column here can't be just integer. We have to say what both of the types are. So we're going to start using lists instead of words as the label for the rows of this table. So we're going to say something like integer, integer. And the next row might be the list integer, rational, and so on. Okay? 16 of these down to complex, complex. If we do this, of course, we're going to be uniform in the way our table works. So we're going to use lists even if for the operators with 1 operand. So that our operate procedure, which in the book is called apply generic and works for this 2 operand case, has a consistent theory about what it's looking for. Okay, so if types are these words, integer, rational, real, complex, and we put them together in a list, that is called a type signature. And those of you who've used languages that call themselves object-oriented but don't believe in message passing will be familiar with that term, that a procedure that you write has a type signature, which is all the types that you declare for all the arguments of that procedure. Okay? So that's a type signature. It can be, it could be 3 operands. The system is extensible to solve any problem. By the way, speaking of numbers of operands, there's another little table. In the literature, mostly, you will see something with 1 operand called a unary operator, something with 2 operands called a binary operator. That's what almost everybody calls them. The problem with this nomenclature is that you all know that binary means something completely different in the context of computers. Right? It means 1s and 0s. And there's nothing about an operator like plus that has 2 operands that has anything to do with 1s and 0s. You might not know that unary also has a similar related meaning in computer science. You might not know that because base 1 seems like a strange idea, but there actually is such a thing, and you'll learn about it in, I guess, 170, or maybe 70. So these names aren't very good. They're confusing. And so, cool people call these monadic and dyadic operators. These names were proposed by Ken Iverson, who invented the important but obscure programming language APL. And they're great names, and they don't have any other confusing meanings. Okay, so now we're doing dyadic operators, and so we have these type signatures. So just for minus, we need 16 of them. And if we want to do plus, minus, times, divide, that's 64 cells in this table to keep track of. That's a real pain in the neck. And people mostly would rather avoid that kind of work. And we can avoid that kind of work if we're observant. And we notice that numbers have a special property. Namely, here's the integers. All integers are rational. Right? So the integers are a subset of the rationals. All rationals are real. Lots more reals than rationals, but every rational number is a real number. And furthermore, oops. Every real number is a complex number, right? Now, notice, by drawing this chart in this way, I have done something that many programming language designers don't seem to understand. So they think that 3 and 3.0 are two different entities. But that's not true. 3.0 is an integer. Maybe it's represented differently in the computer, but that's the computer's problem, not yours. Mathematically, 3.0 is the same number as 3. And your language ought to think in those terms. Because the purpose of computer science is to enable you to solve problems with computers without thinking about computers, without knowing anything about computers. Just thinking in the language of the problem you're trying to solve. So that's sort of the forward march of computer science, is you having to think less and less about how they represent things inside the machine, and instead spend time thinking about the problem you're trying to solve. Okay, so we're going to take advantage of the fact that these 4 numeric types happen to form a nested sequence of bigger and bigger sets. And we're going to do it this way. First, we're going to find our chalk. There we go. We're only going to have 4 rows for numbers in the table. So we're going to forget about type signatures, and we're just going to have integer, rational, real, complex. And if you remember the way they build up these types in the book, for minus, to subtract 2 integers, we just use schemes minus. And for rational numbers, we had something called minus rat. And for reals, we just used schemes minus. And then for complex, we had something like complex minus. Or maybe it was just C minus. Right? Well, what if we get an integer minus a rational? What do we do in that case? Well, the next thing we're going to do, besides plus minus times divide, we're going to have 2 more columns in our table. One is called raise, and one is called level. Okay? Level is going to be used to tell us about this subset relationship. What's a subset of what? And the way it's going to do that is we're not even going to put procedures in here. We're just going to put 1, 2, 3, 4. Okay? Bigger number, bigger set. Okay. Raise says for each level, how do we convert this to the next level up? Okay, so this is going to be n maps to make rat n1, right? To get an integer to a rational number, we do integer divided by 1. That's a rational. Okay? The raise procedure for rational has to raise it to a real number. And how do we do that? We do rational number maps to divide the numerator of R by the denominator of R. Okay? So this gives us a floating point representation of that integer, because this is the scheme built-in divide. Actually, when I say that, I'm lying. We went to some pains to make sure that when you say slash, what you get is not an exact rational, because many versions of scheme, probably most by now, actually do support exact rationals as a built-in type, but ours doesn't on purpose so that I can give this lecture. To raise a real number to a complex number, what do I do? X maps to make complex x 0, right? So it's x plus 0I. Or if you're an electrical engineer, x plus 0j. Complex, we leave this slot empty. There's nothing in here, because there's nothing to raise complex to. That's as far as we get. Okay? So now, we're calling a dyadic operator. We get two operands. We extract their types, and that gives us a type signature. So what our operate procedure has to deal with is still, to begin with, a type signature. Then what it's going to do is for each word in that type signature, it's going to look up level. So if we have, let's say, an integer and a rational, we get back 1 and 2 respectively. Okay? Whichever of those numbers is smaller, we look up raise for that data type and apply it to the value that we have. So if what we have is an integer, well, let's say an integer plus a complex, just to make it more interesting. So I have an integer and a complex, and the answers are 1 and 4. 1 is smaller, so I call raise on my integer. And that gives me an exact rational. Like, let's say it's 5. I get 5 over 1. Okay? Well, now I recursively call apply generic, which is the book's name for what I've called operate here. And now I have a rational and a complex, so we look at their types. We look at their types, rational, complex, and then we map level on that type signature, and we get 2, 4. The levels are still not equal. So I do the same thing. I find the smaller level, which is the rational number, and I call raise on it. And that converts it to a real number. So I started with 5, and then I had 5 over 1, and now I have the thing that prints as 5.0, which is 5 in real representation. And now I recursively call apply generic, and I have a real and a complex, and I look at their levels, and that's 3 and 4. Still not the same. So I take the smaller one, which is 3, and I raise that operand again. Now it's a real number that I'm raising, so I say make complex 5.0, 0, and I get the answer 5.0 plus 0I. And now I call apply generic again, and we look at the levels of the two types. The two types are now complex, complex. So their levels are 4, 4. They're the same. So now I can go ahead and look up how to subtract two complex numbers and apply that procedure to the two numbers. Okay, questions about that? Yeah. Okay, good question. His question is, what if instead of just raising one level at a time, I make procedures for every pair of types that raise the smaller one to the higher one? We could do that. it would give us 3 plus 2 plus 1, 6 procedures to write instead of 3. That's not the end of the world, 6 compared to 3. But it's a little more elegant since these things are subsets of each other to kind of take advantage of that. But we could do it that way, you're right. So we could have type signatures in the table only for the raise operator. And that would directly raise integer to complex or whatever. That would actually be better in one way because this mechanism that I've just described to you has a drawback. And that is, if I take the exact rational number 1/3, or even, it turns out, the exact rational number 1/10, and convert that to real number computer form, I get an inexact answer. Right? With 1/3, that's true even for ordinary decimal elementary school arithmetic. You get 0.33333333, etc. Right? And so if we represent it internally as 0.333333, that's not exactly right. You will learn a little bit in 61C about the fact that not exactly right answers cause a lot of trouble. Because you're thinking, well, 0.333333, that's close enough. That's more precision than I care about. But that's true if you only ever do one operation on your data. Typically what happens in a numeric, especially in scientific computation, is you multiply that 1/3 by something, and you add something else, and you divide by something else, you add something else, and you subtract 1/3, and you get something that's like way wrong. Well, I'm sorry, no you don't. You get something that's way wrong if you do something like taking the tangent of one of these inexact values. Why? Because the tangent function has a huge slope, right? Everybody remember that from high school? Zoop, and then goes back down here and goes zoop again, right? So except for right near those zero crossings, a teeny little error in the argument to tangent turns into a huge error in the return value from tangent. Okay, and if you use that in a more complicated computation and that error propagates, before you know it, you have 0 digits of precision. Avoiding that is the job of a field called numerical analysis, which very few people actually choose to go into. But it's important that some people go into it because otherwise our next generation of computers will just produce crazy wrong answers, which is what used to happen until Professor Kahn in our department sort of laid the groundwork for dealing with imprecision in computers in a systematic way. Okay. So, yeah, it would be a little bit better if we wanted something like, if what we really wanted to do is raise our rational number to complex, it would be better if we could make it 1/3 plus 0i, or with an exact 1/3 as the real part. That's a little bit tricky because it's no longer the case that the components, real part and imaginary part, of our complex numbers are just plain old numbers, which is what the implementation of complex numbers in the book assumes. Right? It assumes that you can just do plain old plus, minus, times, divide on real part or imaginary part of a complex number. So now we have to take a real part and imaginary part and do this complicated thing just in case the real part is an exact rational rather than an inexact real. Okay? So the sort of bottom line answer, I've given a very long answer to this very simple question. The bottom line answer is there's no way to do it that is perfect in every respect. You can do it absolutely perfectly as far as the results are concerned by having 16 rows in the table for all the different type signatures. But that drives your programmer crazy. So instead, we want to take some shortcut. And the simplest shortcut is this one I presented here, where we just have one raise operator that raises by one level, and we keep calling that until we get to the same level. But a slightly more complicated way would have 6 raise operators, and you would look at the type signature to decide which one to use. And then 4 of each of the arithmetic operators, plus, minus, times, divide. Okay? Okay, so one more thing on this subject of raising, and that is we're really lucky that these numeric types form a nest of subsets of each other as they do. That isn't the case in every situation, and the book gives the example of shapes where, as part of the universe of shapes, we have quadrilateral, and then there are various special kinds of quadrilateral, like, for example, parallelogram and trapezoid. I think it makes much more sense if you consider parallelograms to be trapezoids, but none of the books do that for reasons that escape me. And there's other ones like kite that are special. And then underneath parallelogram, there's a thing called a rectangle. And then there's a different thing called a rhombus, which, in case you've forgotten high school geometry, is a parallelogram in which all the side lengths are the same. And then there's this thing called square, which is both a rectangle and a rhombus. It has equal sides and right angles. So what should the raise operator do for a square? Well, it depends what we want to combine it with. What does it mean, by the way, to combine shapes? What kind of operation would you ever want to do that combines shapes? Answer. You're writing a computer program that does some kind of graphics, and sometimes you have a shape like this, and then you want to put another shape overlapping with it. And you'd like the result to be this. Okay? So you see this one on top of that one. In order to do that, you need to get a handle on this shape, which is the set difference between the rectangle and the square. So it's rectangle minus square, in a certain sense, is what this shape is. In the set theory kind of minus, though, not the numeric kind of minus. But in order to do that, this is a square, this is a rectangle, I have to raise it. It's also perfectly possible that I might have had a rhombus over here, and I want to overlay that with a square. And now I have to do a somewhat different calculation to get the result that I want. Okay? So this picture that I'm drawing on the top board now is something that actually comes up in writing computer programs, if they have anything to do with graphics. Well, if they have anything to do with versatile graphics. For many ordinary purposes, we solve the problem by having no shapes other than rectangle. And that, by the way, is also a solution to the numeric problem. We could decide to have no numbers other than complex. So if you type in 3, we represent that in the computer as 3.0 plus 0.0 I. If we do that, then there's never any issue about types at all, and we don't have to go through this. The cost of that, again, is that you can't have exact rational pieces to a complex number. You lose precision that you could have kept. So systems that use numbers just a little bit might decide to do this thing about only complex numbers internally. But if you're writing something like Mathematica or MATLAB, which some of you will have used, where numbers are really, really crucial to your work and you want to get the very best answer you possibly can, then you really do have to have exact rationals as a data type. And you have to go through all of this that we're talking about. OK, questions? No. Have I forgotten to say anything? No. See you next week.